Alrighty, so today I'm going to walk you through the process of doing problem number 10.6 out of the book. So if you read the problem, an ideal vapor compression refrigeration cycle operates at steady state with refrigerant 134A as the working fluid. Saturated vapor enters the compressor at 2 bar, and then a saturated liquid exits the condenser at 8 bar. The mass flow rate of the refrigerant is 7 kilograms per minute. Be sure you pay attention to that. Determine the compressor power in kilowatts, the refrigerating capacity in tons, and the coefficient of performance. So it's good practice to, once you've read the question, is to go ahead and set up your different states. So we've got state 1, state 2, state 4. So we know right off the bat that for the pressure for state 1, the pressure equals 2 bar, and we also know that it is a saturated vapor, so state 2, we know from the problem after it goes through the compressor is at 8 bar. So that means that by default, state 3 is 8 bar as well. And state 4, because it is directly coupled to state 1, there's no pressure change in the evaporator, state 4, is 2 bar. So now we can go through our property tables, or handy dandy property tables, go up and look at for refrigerant 134A. For state 1, right off the bat, we can get the enthalpy, and because it's a saturated vapor, we just need the enthalpy of the gas, Hg. So that's 2.41.3 kilojoules kilogram. And we also can get the entropy, again, from the gas. Probably should give myself a little more space there. Yeah, that's beside the point. Anyway, now, because this problem is nice and pretty, we don't have to worry about any isentropic inefficiencies in the compressor. So the entropy at state 1 is the same as the entropy at state 2. So S2 equals 0.9253. And then the other ones that we can get directly off the tables is state 3. Hold on one second. Let me move this around. So state 3 at 8 bar, H3 equals 93.42, because in the problem it says that state 3 is a saturated liquid. And through the expansion valve, the H3 equals H4, so H4 was 93.42 as well. Now back to the enthalpy at state 2, we're going to have to interpolate from the superheated tables. So I've clipped them and added them in right here. So the interpolation is relatively easy. This is the formula for interpolation. Pretty straightforward. So this is the lower bound for y. This is your x that you're trying to get the data for. This is the lower bound for x, upper bound for y, and upper bound for x. So plugging in values from this table, you get something that looks like this. right, and running that through your calculator, you get H2 to equal to 269.92. We're going to add that to our little state table. Alright, so now that it's pretty much all filled out, we don't have to worry anything else about with entropy, because this is a nice happy problem. We've got all of our enthalpies, all of our pressures, everything else. We don't need our temperatures. So now we can start solving. So for part A, as part A says, we're looking for the compressor power. So A will dt Q minus W I'm simplifying it a little bit here, just so that for the interests of time. Oops. It's H2 minus H1. And so this is for the work input of the compressor. So rearranging and getting rid of things that are equal to 0 or that don't apply, we get work, control volume, or work of the compressor, excuse me, H2 minus H1. Now the mass flow rate is given to us as 7 kilograms per minute, so we have to change that to second for the kilowatt, because kilowatt is in units of seconds rather than minutes. So we do simply 70 over 60 for our indot. So the problem now becomes 7 over 60 times 269.92 minus 241.3 4. And when you solve that, you get the work of the the compressor equals 3.339 kilowatts. So now moving on, we're looking for the refrigeration capacity for part B. So again, I'm skipping over some steps with the rearranging of the second law, or first law. So Qn equals m dot H1 minus H4, because that is the change, and if you go back up here, that is the change in enthalpy between 4 and 1, which is the energy taken in by the evaporator. So that tells us how much it can refrigerate. So again, but now refrigeration capacity is given in units. The units require minutes, because one ton equals 211 kilojoules per minute. So plugging in all of our values. Solving equals 1035.16 kilojoules per minute. And so now for the capacity, we have to divide that by the 1 ton conversion. So 1035.16 divided by 211. This is kilojoules per minute. And so that leaves us with refrigeration capacity of 4.9 tons. And lastly, our coefficient of performance, part C. Coefficient of performance is given by this equation. B equals the refrigeration N, the heat N, divided by the work of the compressor. And so now we have the heat that it takes in, kilojoules per minute, and we know the work of the compressor as 3.339 kilowatt, so we need to convert this one to minutes, or to seconds, sorry. So we'd simply divide by 60. So I'm going to go ahead and do that in the next equation. So we're going to do the work in, or the heat in, over 60, and divide that by the 3.339, and that will give us a coefficient of performance of 5.167. And that is how problem number 10.6 is solved.